Welcome to the channel. Today's video is a calm deep dive into Earth during the age of Pangea, one of the deadliest intervals in our planet's history. If you enjoy this kind of science documentary, please remember to like the video, subscribe, and share it with someone who loves learning about ancient Earth. Thank you so much for spending your time here. I'm really curious, what time is it for you right now, and where are you listening from? Let me know in the comments below. Far from the noise of any surface, the solar system lies in deep and nearly unchanging darkness, and in its centre, the sun shines with a steady light that has already burned for billions of years and continues through the age when Pangea exists as a single joined continent on Earth. The star is an ordinary yellow sun in astronomical terms, massive enough that its gravity holds a family of planets in regular paths, but quiet enough that its energy output changes only slowly over geologic time, so each world moves through space along a path that repeats with patient consistency. The inner planets trace small ellipses close to the sun, while the giant outer planets follow larger, slower tracks, and this entire structure sits inside a wider cloud of icy bodies and distant debris. On the scale of the galaxy, this system is only one of many, but for Earth and its long history, the solar system is the stable stage on which supercontinents form and break apart, oceans open and close, and ancient species appear and vanish. Pangea belongs to one chapter in this larger planetary story, yet from the vantage point of space, it is simply a change in the pattern of light and dark that covers one small world. As Earth travels round the Sun, its orbit is close to circular, so the total energy it receives during a year remains nearly constant, and this helps keep the long-term climate of the planet within limits, suitable for liquid water and for life over hundreds of millions of years. Small variations in the shape of the orbit, in the slow wobble of the axis, and in the tilt of that axis relative to the orbital plane do occur, but these changes act over tens of thousands to hundreds of thousands of years, and in the time of Pangea they simply add gentle cycles to the larger background of solar input. From afar, Earth appears as a bright, slightly bluish point of light that follows its path in about one Earth year, which is the time it takes to complete a full circuit around the Sun. The planet spins once every roughly 24 hours on its tilted axis, creating the familiar alternation of day and night, and that rotation rate and tilt are already well established by the time the continents have merged into Pangea. The tilt means that different latitudes lean toward or away from the Sun at different times of the year, and this produces seasons, but from the perspective of space, these seasonal changes show up only as slow shifts in the pattern of cloud belts, ice and dark land across the disk of the planet. During the age of Pangea, the positions of the continents are different from later times, yet the orbital path and the basic tilt of the axis remain within the same broad ranges that hold throughout much of Earth's history. The supercontinent stretches across a wide span of latitude, so its outline in space covers high and low latitudes in a single continuous block, while the surrounding global ocean of Panthalassa wraps almost all the way around it as a dark light scattering ring. Because the planet rotates once each day, a band of sunlight moves smoothly across this joined land mass and its encircling waters, and from high above the path of the Sun, over the course of a year can be traced as a shifting bright zone that migrates from one hemisphere to the other. Over very long intervals, slow gravitational interactions among planets slightly alter Earth's orbit and axial orientation, and these orbital cycles modulate how sunlight is distributed among latitudes and seasons, including during the time when Pangea dominates the surface. Yet even while continents drift and crustal plates rearrange, the scale of these orbital variations stays small compared with the total energy Earth receives, and the Sun continues to bathe the planet in a relatively stable stream of light. In the sky above Pangea, the Sun rises and sets with the same apparent size and brightness seen in many other eras, because the average distance between Earth and Sun is nearly unchanged, and so the power of the solar radiation reaching the top of the atmosphere remains in the same general range. Seen from space, night covers half the planet at any moment, and in that hemisphere the outlines of Pangea and Panthalassa vanish into darkness, broken only by lightning and the faint glow of starlight, while on the day side the contrast between the large connected land and the wide ocean boundary stands out under the sun's illumination. High above the orbits of weather systems where the thin upper atmosphere gives way to near vacuum, the planet's magnetic field guides charged particles and shapes, faint auroras near the poles, but these lights, like the shifting clouds and moving ice, are small surface details when compared with the overall stability of the Earth-Sun distance and orbital pattern. Far beyond the Sun and its planets, drift around the centre of the Milky Way galaxy in a broad, slow orbit that takes on the order of hundreds of millions of years to complete. So during a single circuit, the planet can pass through several cycles of supercontinent assembly and breakup. The age of Pangea occupies only a segment of this galactic path, yet within that span the view from space is dominated by a single connected landmass, turning under the same star, following the same nearly circular track, and maintaining conditions that allow liquid water to persist at the surface. From this outer vantage, changes that matter most to climate and life arise within the thin shell of rock, water and air that coats the planet, while the deeper orbital setting of the Earth-Sun system continues on with quiet, predictable motion. During the time when Pangea spans much of one hemisphere, this stable astronomical framework sets the overall energy budget of the planet, and any later variations in surface conditions must work within the limits imposed by the distance to the Sun and the timing of Earth's path around it. In the age of Pangea, Earth continues to move along a path around the Sun that is set by gravity and by the distribution of mass in the solar system, and this path controls how solar energy reaches the planet over long spans of time. The orbit is not a perfect circle, but a gentle ellipse, so the distance between Earth and the Sun changes slightly over the course of a year, and this changes the amount of energy arriving at the top of the atmosphere by a modest fraction. When Earth is a little closer to the Sun, the incoming radiation is slightly stronger, and when it is farther away, the flux is slightly weaker, but the differences are small enough that liquid water remains stable on the surface, and life can persist through many cycles of orbital change. Over tens of thousands of years, the shape of the orbit slowly shifts as the gravitational pull of other planets, especially Jupiter and Saturn, gently tugs on Earth. This gradual change in orbital shape is called eccentricity, and during the late Paleozoic and early Mesozoic, it cycles between states with a more circular path and states with a slightly more stretched path. Each state slightly alters the distribution of solar energy between seasons, setting up long-term pacing for warmer and cooler intervals that can leave traces in rocks ice formed at high latitudes and the pattern of sediments laid down in ancient basins. At the same time, the tilt of Earth's axis, known as obliquity, determines how strongly the Sun's rays strike different latitudes over the year. A larger tilt sends more intense summer sunlight into high latitudes and leads to stronger seasonal contrast between summer and winter, while a smaller tilt softens that contrast and spreads solar energy more evenly between the equator and the poles. During the time of Pangea, obliquity varies within a range similar to that of later times, and these variations occur on timescales of tens of thousands of years. The combined effect of tilt and orbital shape means that the pattern of seasons and the strength of summer heating in various bands of latitude are not fixed, but drift slowly through cycles that repeat many times while the supercontinent remains assembled. Another slow movement called precession changes the direction in which Earth's axis points in space, while the tilt angle itself stays nearly the same. Precession operates on timescales of around tens of thousands of years and shifts the timing of when each hemisphere leans toward the Sun along the orbit. As a result, in some long intervals, the northern hemisphere receives stronger summers when Earth is a bit closer to the Sun, while in other intervals the southern hemisphere does so instead. During the Pangean interval, these precession cycles cause gentle but important changes in how solar energy is distributed between hemispheres and between seasons, adding another layer of variation to the climate backdrop against which the supercontinent's environmental conditions unfold. The total power of sunlight at Earth's distance is often described as the solar constant, which is the average flux of energy arriving at the top of the atmosphere when the planet is at its mean distance from the Sun. In the late Paleozoic and early Mesozoic, the Sun is slightly less luminous than it is in more recent geological time, because stars like the Sun brighten slowly as they age by changing their internal structure and fusion rate. The difference in output on the timescale between earlier supercontinents and Pangea is modest but real, so the solar constant during the age of Pangea is somewhat lower than at present. This means that all else being equal, the planet would receive slightly less energy at the top of its atmosphere, but other factors such as greenhouse gases and the arrangement of land and sea determine how much of that incoming energy is kept near the surface. The spatial distribution of solar energy is not uniform across the globe. The equatorial region receives more direct sunlight, because the sun's rays strike there at a higher angle, whereas toward the poles, the same energy is spread across a larger area and the rays pass through a thicker slice of atmosphere. This basic geometric pattern holds during the age of Pangea, just as in other eras, so the equatorial belt tends to have high mean solar input, while polar regions receive lower average energy and are more sensitive to seasonal and orbital changes. Superimposed on this geometry, the eccentricity, tilt and precession cycles shape the details of how much sunlight reaches each latitude in each season, and these details can influence the growth or retreat of ice sheets, the strength of monsoon systems, and the frequency of climatic extremes. From the standpoint of deep time, the orbital cycles repeat with a regular rhythm that interacts with slower tectonic processes. Plate motions that build and maintain Pangea operate over tens to hundreds of millions of years, while the orbital cycles run many times within that interval, constantly modulating the seasonal pattern of solar radiation at the surface of the supercontinent and its surrounding ocean. Sedimentary rocks laid down in basins along Pangea's margins and in its interior preserve rhythmic layers that match the pacing of these orbital variations, suggesting that the cycles in solar input leave a clear record in changing lake levels, shifting shorelines and alternations between wetter and drier or warmer and cooler intervals. Even so, the range of orbital forcing remains bounded by the physics of the Earth-Sun system, and it does not push the planet into states completely outside the broad conditions that allow liquid water to persist. In the context of Pangea, this means that while orbital parameters can strengthen or weaken seasonal contrast and shift climate belts slightly north or south over long spans, they act on top of the more fundamental boundary conditions set by the presence of a single joined continent and a nearly encircling superocean. At any instant in the age of Pangea, a map of incoming solar energy at the top of the atmosphere shows bright bands near the equator, where midday sun stands high in the sky, and dimmer zones toward the poles, where the sun remains low, as well as seasonal migration of these bands as the tilted planet moves along its orbit. Over thousands of years, that map gently breathes as the orbital parameters drift through their cycles, adjusting the contrast between seasons and the relative warmth of hemispheres. Throughout, the total annual energy received by the planet stays close to constant, because the mean distance to the Sun and its average luminosity alter only very slowly. In the age of Pangea, these slow predictable changes in solar input operate continuously, while the continents remain joined, setting the outer boundary conditions for any surface environment that develops on land or at sea. During the time when Pangea dominates Earth's surface, the planet is wrapped in a continuous shell of air that extends upward for many tens of kilometers, thinning with height, but always tied to the ground by gravity. This global atmosphere is made mainly of nitrogen and oxygen, with smaller amounts of argon, carbon dioxide, water vapor, and trace gases. Nitrogen is an inert background gas under most conditions and makes up the bulk of the air, while oxygen produced and maintained by long-term biological activity supports respiration and many chemical reactions at the surface and within the lower atmosphere. Carbon dioxide is present at levels that are higher than many later intervals in Earth's history, though estimates vary, and it acts as an important greenhouse gas, trapping some of the outgoing heat that the planet radiates back to space. Water vapor is highly variable in both space and time, concentrated in the lower atmosphere, and especially in warm regions and over the oceans, and it plays a central role in cloud formation, precipitation, and the transfer of energy through condensation and evaporation. Near the ground, the lowest layer of the atmosphere, called the troposphere, contains most of the mass of air and almost all of the water vapor. In this layer, temperature generally decreases with height, and it is within this zone that clouds form, storms build, and winds interact directly with the land and sea of the Pangean world. The thickness of the troposphere is greater over warm regions and smaller over cooler regions, but in general it extends up for several to many kilometers before reaching a boundary called the tropopause. Above the tropopause lies the stratosphere, a more stably layered region, where vertical mixing is weaker and temperatures can increase with height, because ozone and other gases absorb ultraviolet radiation from the sun. In the time of Pangea, the exact amount and vertical distribution of ozone are still subjects of study and uncertainty, but there is good evidence that an ozone layer is present and provides significant shielding of the surface from the most harmful, short-wavelength solar radiation. This protective layer allows complex land ecosystems and shallow marine communities to function under levels of ultraviolet light that are not immediately destructive, even though regional fluctuations may occur during episodes of strong volcanic gas release or other disturbances. Higher still, the atmosphere grades into even thinner layers such as the mesosphere and thermosphere, where air density becomes very low, and particles and molecules interact directly with incoming solar and cosmic radiation, but these upper layers hold little direct influence over day-to-day surface weather. Throughout the atmosphere, the pressure of the air decreases with height, because there is less mass of gas above any given level, and the density follows this decline. Near the surface of Pangea and Panthalassa, pressure and density are sufficient to support a vigorous system of winds, clouds, and storms, driven by uneven solar heating and by the rotation of the planet. The composition of the atmosphere during the late Paleozoic and early Mesozoic reflects a balance between several processes including volcanic degassing, chemical weathering of rocks on land burial, and oxidation of organic matter and exchange of gases with the ocean. Volcanic eruptions release carbon dioxide, water, vapor sulfur gases and other components into the air, adding greenhouse gases, and particles that can affect climate on timescales from years to millions of years, depending on the scale and frequency of activity. Chemical weathering of silicate rocks on the exposed surfaces of Pangea removes carbon dioxide from the atmosphere over long spans, converting it into dissolved ions that rivers carry to the sea, where they eventually form carbonate minerals. This silicate weathering feedback is sensitive to temperature and rainfall, so as the climate warms, weathering can accelerate and draw down carbon dioxide, while cooler, drier conditions can slow the process. Living organisms also influence atmospheric composition. Land plants take in carbon dioxide and release oxygen through photosynthesis, while respiration and decay consume oxygen and return carbon dioxide to the air. During the late Paleozoic, vast swamp forests and widespread vegetation store significant amounts of carbon in soils and sediments, and as conditions shift into the early Mesozoic and through the time when Pangea is assembled, patterns of vegetation wildfire and erosion, adjust the balance between carbon storage and release. The net effect is an atmosphere in which carbon dioxide is elevated enough that together with water vapour, it strengthens the greenhouse effect and contributes to globally warm conditions, even though regional climates on the supercontinent can differ strongly between coast and interior. Oxygen levels in the atmosphere during the late Paleozoic reach, values higher than present for significant intervals, with some estimates suggesting considerably enriched oxygen compared with later times, but across the Permian and into the Triassic, there is evidence that oxygen may decline. The exact timeline and magnitude of these changes remain under study and estimates differ, yet the general picture indicates that atmospheric oxygen is still sufficient to support complex terrestrial animal life and large active vertebrates living on land in the Pangean world. Small amounts of trace gases including methane nitrous oxide and various sulfur compounds also play roles in atmospheric chemistry and climate, but their concentrations are more uncertain and may fluctuate in response to biological activity and episodic events, such as large volcanic eruptions or changes in sea level. Aerosols, which are tiny particles or droplets suspended in the air, come from volcanic eruptions, desert dust, sea spray, and combustion, including wildfires. These particles can reflect or absorb sunlight and act as nuclei around which cloud droplets form, so they influence both the amount of solar radiation reaching the surface and the properties of clouds. In a world with a large interior desert and frequent volcanic activity in some regions, dust and volcanic aerosols can be important components of the atmosphere, at least episodically altering the clarity of the sky and the amount of sunlight that reaches ground level. The vertical structure of temperature and wind within the atmosphere over Pangea is also shaped by the rotation of the planet. The Coriolis effect, which arises from rotation, deflects moving air to the right in the northern hemisphere and to the left in the southern hemisphere, helping to organize large-scale wind patterns and jet streams in the upper troposphere. These jets form where strong horizontal temperature gradients appear, such as between warm tropical air and cooler polar air, and they tend to flow from west to east. Above the joined landmass of Pangea and the encircling waters of Panthalassa, these high-altitude winds steer storm systems, influence the development of high and low pressure regions, and interact with the underlying topography and distribution of land and sea. The atmosphere also contains water in all three states, vapor, liquid, and ice. Clouds are made of tiny droplets or ice crystals that form when moist air rises, cools, and reaches saturation, and their distribution over Pangea and Panthalassa is controlled by where air ascends or descends within the global circulation. Precipitation falls when these droplets or crystals grow large enough to overcome air resistance, returning water to the surface in the form of rain or snow. Evaporation from the surface of the superocean and from lakes, rivers, and soils on land returns water vapor to the air, closing the hydrologic cycle. In the Pangean world, this cycle continues without interruption, but its regional expression strongly depends on the arrangement of the continents, the presence of mountain ranges, and the distance from the sea. All of these processes operate within the bounds of the global atmosphere, which acts as both a thin protective shell and a dynamic fluid layer that connects the sun's energy to conditions on the surface of the supercontinent and its surrounding ocean during this interval in Earth's history. During the age of Pangea, the flow of energy from the sun into the atmosphere sets up broad climate belts that wrap around the globe, and within those belts large circulation cells carry heat, moisture, and momentum through the air. Near the equator, intense solar heating warms the surface and the air just above it, causing that air to rise and expand, and as it rises it cools and loses some of its water vapor as clouds and precipitation. This rising branch of motion forms a band of frequent upward movement and cloudiness that tends to follow the region of higher solar input, and together with the return flow at height, It defines the core of what is known as a Hadley cell. Air that has risen in this equatorial region spreads poleward in the upper troposphere, moving away from the equator on both sides as it transports heat to higher latitudes. Eventually, this upper-level air cools, becomes denser, and begins to sink in subtropical belts, creating broad zones of descending motion. As the air sinks, it warms by compression, its relative humidity falls and clouds become less frequent, so these subtropical belts tend to be regions of clear skies and higher net solar input at the surface. At the bottom of the atmosphere, this pattern of rising air near the equator and sinking air in the subtropics closes a circulation loop because air that has descended in the subtropics flows back toward the equator near the surface. The rotation of Earth deflects this flow, turning the equatorward movement into prevailing winds that blow from east to west in the tropics on both sides of the equator. These are the trade winds, and they carry heat and moisture across low latitudes, shaping where clouds and rainfall occur. Farther poleward, roughly in what are now called the mid-latitudes, the circulation pattern differs. Here air tends to move from west to east as part of another set of circulation cells, often described as feral cells, that lie between the subtropical belts and polar regions. In these zones, temperature contrasts between warm air from lower latitudes and cold air from higher latitudes generate strong horizontal gradients. The atmosphere responds with large rotating weather systems known as cyclones and anticyclones, which act to mix air masses and transport heat poleward. Along the boundaries between contrasting air masses, fronts form and bring changing weather and bands of clouds and precipitation. Above these mid-latitude regions, narrow streams of fast-moving air. The jet streams follow the paths of steepest temperature change in the upper troposphere and help steer weather systems along preferred tracks that tend to circle the globe from west to east. Closer to the poles, the circulation is often described as a polar cell, where cold, dense air sinks near the pole and flows outward at low levels, again being deflected by rotation into prevailing easterly winds. This three-cell pattern in each hemisphere, with Hadley-Ferrel and polar cells stacked from equator to pole, represents a useful average description for Earth's atmosphere, though the real circulation is more complex and contains many waves, eddies, and regional features. During the time when Pangea is assembled, this broad structure still applies, because the same fundamental drivers are in place: differential heating between equator and poles, rotation of the planet, and the need to transport heat from low to high latitudes. However, the presence of one dominant supercontinent changes how these basic circulation cells express themselves at the surface. Instead of many smaller land masses scattered across a wide superocean, most of the land area is concentrated into a single body that stretches across a large range of latitudes. This alters where rising and sinking air align with land and sea, and it can shift the positions and strengths of climate belts in important ways. When air rises in the equatorial belt, the associated band of frequent clouds and rainfall can fall partly over the superocean and partly over continental regions, depending on the exact position of Pangea relative to the equator at a given time. Where this belt intersects, land surface conditions tend to be more humid and support more runoff, while where it lies over ocean evaporation and rainfall form part of the marine hydrologic cycle. The descending branches of the Hadley cells in the subtropics also interact with the supercontinent. Sinking warming air favours clear skies and reduced precipitation, and when these subtropical high-pressure belts coincide with broad interior regions of land that lie far from the moderating influence of the sea, they establish conditions that can favour persistently dry climates. Because Pangea extends across both hemispheres, the symmetry and exact latitudinal placement of these belts can differ from those on a world with a more even spread of continents, and modelling studies suggest that strong subtropical highs may become anchored over certain continental sectors for long intervals. In the mid-latitudes, westerly winds blow over both ocean and land, but as they pass over the extensive continental interior, they encounter surfaces that heat and cool more strongly with the seasons than ocean surfaces do. This contrast sharpens temperature gradients along the coasts and helps to organize storm tracks that follow preferred paths where land and ocean meet. The jet streams in the upper troposphere adjust to these gradients, forming broad arcs that tend to undulate along the edges of Pangea and across its mid-latitude sectors. The position and strength of the jets influence how often cyclones travel over different parts of the supercontinent and the surrounding water, and how long they persist in a given region. At high latitudes, polar circulation is affected both by the distribution of land and sea and by the overall climate state. When temperatures are low enough, ice and snow cover can extend the reflective surface area and contribute to cooler local conditions, reinforcing polar cold. When conditions are warmer, the pole to equator temperature contrast can weaken, changing the structure of the polar jet and modifying the behavior of storm systems. In the Pangean world, available evidence suggests a generally warm global climate, with reduced permanent ice compared with later Ice Age states, but there is still a significant gradient between low and high latitudes, and this gradient maintains active mid-latitude weather systems and high-level jets. Across all latitudes, the large-scale circulation has another key role: it redistributes moisture. Air that has lost water through precipitation in rising regions becomes relatively dry as it flows away, and as it sinks it can form belts of low humidity. Other regions where air is forced upward by global circulation or by interaction with surface features tend to be wetter. Over an enormous single continent, the locations where air tends to rise or sink and the paths along which winds blow become crucial for determining which broad regions receive more regular moisture and which experience long-term dryness. The circulation belts also interact with day-length solar angle and seasonal shifts in the apparent path of the Sun. As Earth moves along its orbit and the tilt of its axis makes one hemisphere lean toward the Sun, and then away, the latitude of maximum heating migrates northward and southward over the year. The band of rising tropical air and its associated rain belt move with it, and the subtropical highs, mid-latitude westerlies and polar circulation all respond in a linked pattern. In a world where land and sea are clustered into many separate pieces, these shifts play out over several disconnected regions. In the time of Pangea, the same shift affect a single linked landmass and its surrounding superocean, so the seasonal migration of climate belts can have particularly broad consequences across connected regions. The global circulation thus serves as a bridge between the outer setting of solar energy and the more local conditions that arise on land and at sea, setting up broad zones of rising and sinking air, prevailing winds and storm tracks that organize the climate of the Pangean Earth. Around the joined land of Pangea stretches a single dominant ocean that covers most of the planet's surface. This superocean, often called Panthalassa, occupies a continuous basin that wraps almost fully around the globe, broken only by smaller interior and marginal seas that lie between and around fragments of continental crust. The basin floor is made of oceanic crust that forms at mid-ocean ridges, where tectonic plates pull apart and new material rises from the mantle, then cools and spreads outward as it moves away from these ridge systems. Over millions of years, this spreading carries seafloor toward deep subduction zones at the margins of plates where it eventually sinks back into the mantle. In the time of Pangea, this cycle of formation and destruction of oceanic crust continues, so ridges, fracture zones, and trench complexes are all present beneath the waters of Panthalassa, defining the shape of the basin and the pattern of its depths. Near the mid-ocean ridges, the seafloor stands relatively high because it is young, warm and buoyant. As it ages and moves away from the ridges, it cools, contracts and deepens, forming broad abyssal plains at depths of several kilometers. These plains make up much of the Panthalassan floor. In places underwater, volcanic activity builds large seamounts and plateaus, some of which rise close to the surface and can form island chains. At the edges of the supercontinent, the oceanic crust bends downward into trenches where subduction occurs, and above these zones, arcs of volcanic islands or coastal mountain belts can grow over time. Along the boundary between Pangea and Panthalassa, the continental crust meets the ocean basin at passive and active margins. Passive margins are quieter edges where the continental crust thins gradually into oceanic crust, with a wide continental shelf and slope, while active margins involve subduction, deep trenches and more intense deformation. Because most of Earth's land area is gathered into one supercontinent, the total length of coastline relative to the area of the ocean is smaller than in times with many scattered continents. This configuration reduces the area of shallow epicontinental seas that typically spread over low-lying continental interiors when sea levels are high. As a result, a larger fraction of the global ocean volume resides in deeper basins and broad shelf regions that would normally host extensive shallow marine ecosystems, occupy a comparatively smaller area. Water circulates through Panthalassa under the combined influence of wind stress at the surface differences in density caused by temperature and salinity, Earth's rotation, and the shape of the basin. At the surface, prevailing winds associated with the global atmospheric circulation drive ocean currents. Trade winds in low latitudes push surface waters westward, while mid-latitude westerlies push them eastward. The Coriolis effect deflects these flows to the right in the northern hemisphere and to the left in the southern hemisphere, so the surface currents tend to form large gyres, which are broad rotating systems of flow. In the subtropical belts of each hemisphere, these gyres circulate clockwise in the north and counterclockwise in the south, concentrating warm water on the western sides of basins and cooler currents on the eastern sides. In Panthalassa, with its wide expanse and fewer interruptions by continents, these gyres can grow to very large scales spanning huge distances and moving significant amounts of heat and salt around the ocean. Equatorial currents flow westward along the warm belt near the equator, and when they encounter continental boundaries or island arcs, they are deflected poleward, forming strong western boundary currents that carry warm water toward higher latitudes. On the eastern sides of oceanic sectors, cooler eastern boundary currents flow equatorward as part of the same gyre systems. These surface currents link distant parts of the superocean, redistributing heat from regions of high solar input toward cooler latitudes and influencing the climate of coastal areas where they meet the landmass of Pangea. In addition to wind-driven circulation, the ocean experiences density-driven flow that depends on the temperature and salinity of seawater. Cold and salty water is denser than warm and fresh water, and where surface conditions allow water to cool strongly or to become saltier through processes such as evaporation or formation of sea ice, that water can sink and help drive deeper currents. In the Pangean interval, patterns of deep water formation likely differ from those in a world with more scattered continents, because the positions of land masses and the overall climate state influence where cold, dense surface waters can form and descend. Once water sinks, it spreads along density surfaces in the deep ocean, gradually flowing toward regions where it can return to the surface through upwelling or mixing. This density-driven circulation is often called thermohaline circulation, and acts over long timescales to connect surface waters with the deep ocean interior, transporting heat-dissolved gases and nutrients vertically as well as horizontally. The shape of the Panthalassan basin and the presence of smaller interior seas influence where upwelling occurs. Where wind patterns drive surface waters away from a region, deeper water must rise to replace them, bringing colder, nutrient-rich water upward. This can happen along some coasts of Pangea, where winds blow parallel to the shoreline in such a way that the net transport of surface water is away from land, or in open ocean divergence zones, where surface flows spread apart. These upwelling regions support higher primary production because phytoplankton gain access to nutrients that have accumulated in deeper layers. Conversely, in regions where surface waters converge, water tends to sink slowly, taking with it some dissolved gases and suspended material. The interior of Panthalassa, far from land-based nutrient inputs, may experience different balances between upwelling and downwelling, compared with smaller, more enclosed seas. The reduced extent of shallow continental shelves means that some nutrients released from land or from coastal upwelling zones may be processed over shorter distances before reaching deep water, and large mid-ocean gyres can become zones of relatively low surface nutrient availability. Interior and marginal seas connected to Panthalassa, such as the Tethys region and other smaller basins, have their own circulation patterns that interact with the main superocean. Narrow gateways and sills between basins can restrict water exchange, so differences in temperature and salinity can develop between these seas and the open Panthalassan waters. In some cases, dense water formed in interior seas may spill over sills into the deeper superocean, contributing to the deep circulation. In other cases, limited mixing can allow stratification to become more stable, with warm, less dense water overlying cooler, denser layers, influencing how well oxygen and nutrients are exchanged with the atmosphere and with surface ecosystems. Over very long timescales, the motion of tectonic plates slowly alters the shape and depth of the ocean basins and the locations of ridges and subduction zones. This gradual reconfiguration modifies the pathways of major currents and the relative areas of different types of marine environments, but throughout the age of Pangea, the central role of Panthalassa as the main reservoir of ocean water remains. Tides generated by the gravitational pull of the moon and the sun also move water and can interact with basin geometry to produce strong tidal currents in some regions, especially where narrow straits or broad continental shelves focus the tidal energy. These currents stir coastal waters and can enhance mixing sediment transport and the supply of nutrients to nearshore ecosystems. Taken together, the structure of the Panthalassan Basin, the pattern of wind-driven and density-driven circulation, and the connection between open ocean and interior seas establish the framework within which marine temperatures, salinities, and nutrient distributions evolve during the time when Pangea is assembled. The resulting patterns of currents and water properties help set the conditions experienced by marine organisms and coastal environments along the margins of the supercontinent and across the vast surface of the global ocean. On the surface of Earth during the age of Pangea, almost all major landmasses link together into one continuous body that stretches across much of one hemisphere, creating a geography that looks very different from later maps with separated continents. The supercontinent itself is often described in terms of two broad sectors, a northern part sometimes called Laurasia, and a southern part sometimes called Gondwana, though in the time when Pangea is fully assembled, these regions are joined without large ocean gaps between them. The northern sector includes what will later become North America, Europe, and much of Asia, welded together along long ancient mountain belts and sutures where earlier continents collided. The southern sector contains the pieces that will one day separate into South America, Africa, Antarctica, India, and Australia. Between these broad pieces lies a zone of complex crustal blocks and smaller basins, including areas that form the foundations of what will later be parts of the Mediterranean region and surrounding territories. To one side of Pangea lies the great expanse of Panthalassa, the superocean that nearly encircles the joined land. On another side, in the broad low latitude and subtropical belt, an important interior and marginal sea system, often called the Tethys region, develops as a long irregular marine passage. This region is made of smaller oceanic tracts, island arcs and narrow embayments that separate parts of the northern and southern crustal blocks, and allows exchange of water between Panthalassa and more enclosed seas closer to the heart of the supercontinent. The overall outline of Pangea on a global map resembles a broad crescent or an elongated cluster covering a wide span of longitude and latitude. In some reconstructions, a large curved margin faces the open Panthalassan waters, while a somewhat more indented side faces the Tethyan basins and related interior seas. The supercontinent extends from high southern latitudes through the tropics and well into the northern mid-latitudes, so a single continuous landmass crosses zones that receive very different amounts of solar energy and experience different seasonal patterns. In what will later become the regions of eastern North America and western Africa, a long junction, once marking the closure of an older ocean, runs roughly along the interior of the Pangean outline still recorded by deep crustal structures and broad mountain belts. These ancient collision zones formed when earlier continents merged give rise to chains of uplands and plateaus that run for thousands of kilometers. In other sectors such as future western North America, parts of present-day Eurasia, and certain southern margins, active plate boundaries along the edge of Pangea produce volcanic arcs and evolving mountain systems where oceanic crust of Panthalassa or Tethyan branches descends beneath the continental blocks. Along many coasts of Pangea, the continental margin is broad and gently sloping, forming wide shelves and low plains where rivers meet the sea. Elsewhere, steep coastal uplands fall rapidly to the shoreline, and narrow shelves drop quickly into deeper water. The balance between these types of margin depends on the history of rifting and collision in each sector. Some regions sit near long-lived passive margins where continental crust thins gradually, and the seafloor deepens smoothly away from land. Other edges are more tectonically active with trenches, island arcs, and deformed belts. This mixture of margin types gives Pangea a varied coastal geography, but the total length of shoreline relative to land area is smaller than in later eras because so much crust is tied into one block. The interior of the supercontinent contains large basins, plateaus, and lowland regions that are separated from the nearest open ocean by thousands of kilometers. In some reconstructions, central and western parts of what will become Asia and interior sectors of what will become North America and Africa occupy these distant inland positions. The ancient cratons, which are stable cores of very old continental crust, underlie broad regions that have experienced only modest deformation for long intervals. Around these cores, belts of younger rocks mark places where smaller blocks have attached to the supercontinent through collision and accretion, building complex mosaics of terrains and mountain foothills. River systems arise in uplands and mountain belts and flow across these broad interiors toward distant marginal seas, or toward Panthalassa, carving long valleys and assembling large drainage networks. Some of these rivers follow structural lows created by earlier tectonic events, while others exploit softer rock layers that erode more easily. Lakes, inland basins, and ephemeral water bodies occupy depressions where subsidence outpaces sediment fill, or where local tectonic stretching has created rift basins that begin to open but have not yet connected fully to the sea. In certain regions along future East African, Arabian, or Central Asian sectors, incipient rifts may start to develop as plate forces change and the crust begins to thin, marking early stages of the processes that will ultimately contribute to the breakup of Pangea. However, for long intervals, the supercontinent remains intact, and these rift zones are simply elongated depressions at or above sea level, sometimes containing lakes or restricted arms of the sea. The latitudinal span of Pangea means that some parts lie near the equator, receiving high average solar input and relatively small changes in day length through the year, while other parts extend into higher latitudes where the sun climbs lower in the sky, and seasonal differences in day length become more pronounced. As a result, the supercontinent can be divided into broad climatic zones aligned with latitude, but the actual conditions on the ground also depend on elevation proximity to the coast and the presence of mountain ranges. Wide lowlands at low latitude along the Tethyan margin differ from higher plateau regions at similar latitudes in the continental interior, even though they share roughly comparable solar forcing. In the southern and northern high latitude sectors of Pangea land extends into zones where winters can be long and dark and summers experience prolonged daylight, even in generally warm global climate states. Coastlines along Panthalassa and Tethyan branches host embayments, inlets and broad bays where seawater reaches into the edges of the supercontinent. These coastal indentations create local variations in shoreline orientation and water depth, which influence where deltas, estuaries and shallow marine platforms can form. Some margins face the open superocean directly with long exposed coasts, while others are sheltered within more enclosed seas where wave energy and tidal range may differ. Island arcs and microcontinents lie offshore in some areas, forming chains that parallel the continental edge, while in other sectors isolated volcanic islands rise directly from the oceanic crust, well away from the main landmass. Over millions of years, the arrangement of these features shifts as plates move, but during the core interval of Pangean existence, the global view is still dominated by a single, nearly continuous continent, with only modest oceanic intrusions into its interior. This geography, with its extensive continuous land, limited shallow seas, on the continental surface, wide interior distances from the coast, and long mountain belts and sutures, sets the physical stage on which regional climates, hydrologic patterns and ecosystems must develop during the time when Pangea holds Earth's major landmasses together. Deep within the joined land of Pangea, far from the moderating influence of the surrounding superocean, the interior of the supercontinent experiences conditions that favour dryness over much of its area for long intervals. Air that has already lost much of its moisture along coastal and near-coastal zones travels across hundreds to thousands of kilometres of land before it reaches the central regions, and during that journey is repeatedly heated and mixed, which further reduces its relative humidity. As a result, large parts of the interior lie under climate regimes where evaporation and transpiration from sparse vegetation exceed precipitation over long time scales, and this imbalance promotes the development of extensive arid and semi-arid belts. In many reconstructions, broad desert regions occupy subtropical latitudes on both sides of the equator within Pangea, and these zones span wide areas of what will later become central parts of North America, northern Africa, and interior Asia. The combination of strong solar heating during long summer days, clear skies over much of the year, and limited access to moist maritime air leads to high surface temperatures during the warm season and large daily temperature swings as heat is rapidly lost at night. In winter, the same lack of nearby ocean moderation allows interior temperatures to fall sharply during cold spells. This pattern of strong daily and seasonal temperature ranges is characteristic of continental interiors and becomes pronounced on a supercontinent of Pangean scale. Within these dry belts, wind plays a major role in shaping the landscape. With limited vegetation, cover-exposed soils and sediments are vulnerable to deflation and transport by moving air. Grains of sand are lifted and bounced along the surface, accumulating into dune fields that can stretch for great distances, while finer silt and clay particles are carried aloft as dust and can travel far across the interior and out over the sea. Over time, shifting dunes produce thick accumulations of wind-blown sandstone with large-scale cross-bedding, which is a pattern of inclined layers that record the migration of ancient dunes. Such deposits are common in rock sequences that formed on Pangea and provide evidence for widespread deserts and arid conditions in its interior regions. Between the dune fields lie gravelly plains, rocky plateaus, and low-relief uplands where weathering acts slowly under dry conditions. Chemical weathering is limited by the scarcity of liquid water, so physical processes such as thermal expansion and contraction salt crystallization in pores, and occasional freeze-thaw cycles in cooler belts fracture rock and produce loose debris. When rare rainstorms occur, water rushes through normally dry channels, moving sediment in short-lived floods. These ephemeral streams may carve shallow valleys and build fans of gravel and sand at the foot of uplands, but they typically run only for hours to days after major precipitation events before returning to dryness. In closed depressions without outlet to the sea, sporadic inflows create temporary lakes that can shrink and vanish under strong evaporation, leaving behind beds of evaporate minerals such as gypsum and halite, along with fine muds that may crack as they dry. These features indicate that in many interior basins, water inputs are irregular and often insufficient to sustain permanent lakes or rivers. Vegetation in the Pangean interior adapts to this regime of moisture limitation and temperature extremes. Plant communities in semi-arid sectors may include drought-tolerant trees, shrubs and seed ferns rooted in soils that store limited water, while more strongly arid zones may host only sparse, low-growing plants or remain largely bare. Soils often develop distinctive horizons, rich in calcium carbonate or other salts, formed when dissolved materials carried upward or downward by small amounts of percolating water precipitate and accumulate over time. These hardened layers, sometimes referred to as calcretes or duricrusts, mark long periods of soil formation under conditions where leaching is weak and evaporation is strong. Wildfires can occur when dry vegetation and litter build up and are ignited by lightning, especially near the margins of dry regions where biomass is sufficient to carry fire. Fire activity influences the structure of plant communities, the cycling of nutrients, and the production of charcoal particles that can be preserved in sediments. The presence of charcoal in some Permian and Triassic deposits suggests that fire is a recurring feature of many landscapes during the age of Pangea, including those transitioning between wetter and drier states. Animals that live in the interior deserts and semi-deserts must cope with limited and variable water sources as well as high daytime temperatures and cooler nights. Some vertebrates likely retreat to burrows or shaded refuges during the hottest parts of the day and are more active during crepuscular or nocturnal periods when conditions are less extreme. Others may concentrate along the courses of intermittent rivers, around spring-fed oases, or near long-lived lakes where groundwater discharge supports more stable vegetation. In this way, the interior arid belts are punctuated by corridors and patches of relatively higher moisture that host more diverse communities, while surrounding expanses remain sparsely populated and open. Sedimentary records from these interiors show alternations between wind-blown sands, ephemeral stream deposits, and lake or playa sediments, reflecting shifts in the balance between dryness and occasional wetter phases over timescales ranging from years to millions of years. Some intervals display thicker accumulations of fluvial and lacustrine sediments, indicating episodes when precipitation increases or drainage networks become more integrated, perhaps due to slow changes in global or regional climate drivers. Other intervals are dominated by aeolian deposits and evaporates, marking times when aridity intensifies and closed basins become more common. Throughout these changes, the controlling factor remains the large distance from oceanic moisture sources and the tendency for descending warming air and clear skies to prevail over central parts of the supercontinent. The overall topography of Pangea contributes to the distribution of dryness by guiding low-level winds and river pathways, but even modest relief can be sufficient to concentrate runoff into certain valleys and basins, while leaving intervening uplands dry. In some regions, long-term subsidence creates spacious sedimentary basins that act as traps for both wind-transported and water-transported material. These basins can host sequences many kilometers thick that archive the history of interior aridity through changing rock types, sedimentary structures, and soil features. Together, the geographic isolation from the sea the structure of atmospheric circulation and the properties of land surfaces combine to make the central regions of Pangea a domain where deserts and semi-deserts occupy a larger fraction of continental area than on many later Earth configurations. Within this dry core, life persists, but must operate under constraints set by heat, scarce water, and frequent exposure of surfaces to wind and radiation, producing landscapes that are open and marked by slow physical change, punctuated by brief, sometimes intense hydrologic events. As the supercontinent of Pangea spans a wide range of latitudes and sites surrounded by the vast waters of Panthalassa and related seas, the contrast between land and ocean heating produces strong seasonal changes in temperature and rainfall, especially along coastal and near-coastal regions. Land surfaces heat up and cool down more quickly than the ocean, because rock and soil have lower heat capacity, and because water can mix vertically and horizontally, distributing absorbed energy through a larger volume. During the warm season in each hemisphere, the parts of Pangea that lean toward the sun receive more direct solar radiation, and the air over these land areas warms more rapidly than the air over the neighbouring ocean. This differential heating lowers surface pressure over the continent relative to the ocean, and encourages moist air from the superocean to flow toward the warmer land. When this moist air reaches the coasts and is forced upward by heating and by local topography, it can condense into clouds and produce intense rainfall. In many reconstructions and climate model results, this pattern is especially pronounced in low to mid latitudes along the eastern and southern margins of Pangea, where warm seasonal onshore winds bring heavy monsoonal rains. The term monsoon in this setting refers to a seasonal reversal in wind direction, associated with large differences in heating between land and sea. And in the Pangean world, such reversals may be stronger and more extensive than in many later continental arrangements, because of the sheer size of the landmass. During the opposite season, when the hemisphere tilts away from the sun and the land cools more strongly than the ocean, the pressure gradient reverses. Surface air over the cooled interior and coastal regions becomes relatively denser and higher in pressure, and winds tend to flow from land towards sea. These offshore winds are drier because they originate over continental regions that have already lost much of their moisture, and as they cross the coast and move over the ocean, they can suppress cloud formation and rainfall over adjacent land areas. The result is a climate pattern in many Pangean coastal zones, where a warm wet season with strong onshore flow and widespread rainfall alternates with a cooler dry season dominated by offshore winds, clearer skies, and reduced precipitation. The intensity of these seasonal swings depends on latitude distance from the coast and the presence of broad topographic features, but the general pattern of monsoon-like behaviour arises from basic physical principles that apply wherever large land masses lie next to extensive oceans. In the tropics and subtropics, where solar input remains high, through much of the year, the warm wet phase of the monsoon can produce large volumes of precipitation in a short number of months. Rivers fed by these rains swell and overtop their banks, spreading water and sediment across floodplains and low-lying basins. Lakes expand and wetlands extend over broad areas. These wet season conditions support more continuous plant cover and soil development compared with the drier interval that follows, when river discharge declines, lakes contract and some smaller water bodies may dry out completely. The alternation of wet and dry phases leaves a distinct imprint in sedimentary records. Layers deposited during the wet season tend to be finer grained and can show structures associated with standing or slowly moving water, while layers formed during the dry season may include features such as desiccation cracks, soil horizons, or coarse deposits from shorter-lived storms. Over many cycles, these seasonal alternations build up thick sequences that record the persistence of monsoonal climates along parts of the Pangean margins. At higher latitudes, seasonal contrasts in temperature and day length are greater, and the interaction between land and sea can generate strong baroclinic storms, which are large low-pressure systems driven by horizontal temperature gradients. In coastal regions of Pangea that lie in mid-latitudes, winters can bring frequent cyclones with strong winds, variable precipitation, and rapid changes in temperature. Summers in these regions may still see monsoon-like flows if land-sea temperature contrasts remain large, but the balance between tropical-style monsoon circulation and mid-latitude storm tracks can vary from place to place. Some coastal belts may be dominated by persistent westerlies and frontal systems rather than by a clear monsoon pattern, especially in more poleward sectors. Even in these cases, however, the presence of a large land mass enhances the amplitude of seasonal changes because continental surfaces respond more quickly to the annual cycle of solar heating than the surrounding ocean. Inland from the immediate coast, seasonal extremes become more pronounced as the influence of the ocean diminishes. Summers can be very hot, particularly in subtropical and tropical latitudes, and the arrival of monsoonal rains may be delayed or reduced, depending on how far moist air can penetrate into the interior. In some regions, strong low-level jets, which are narrow bands of fast-moving air near the surface, can form along pressure gradients between the monsoon low over the land and the subtropical highs over the ocean. These jets can transport moisture and momentum deep into the continental interior, focusing rainfall along preferred corridors while leaving adjacent areas relatively dry. In other regions, subsiding air on the flanks of the monsoon circulation or beneath subtropical high-pressure systems can inhibit cloud formation and produce clear hot conditions even during the nominal wet season. As a result, the spatial pattern of rainfall associated with Pangean monsoons is not uniform but exhibits strong regional contrasts, with some sectors receiving regular seasonal downpours and others experiencing more erratic or limited precipitation. Another aspect of seasonal behavior in the Pangean world is the presence of heat waves and cold spells that arise from persistent atmospheric circulation patterns. When high-pressure systems remain stationary over continental interiors, they can produce extended periods of clear skies, weak winds, and intense solar heating, driving surface temperatures to high values and drying soils and vegetation. Conversely, when cold air masses formed at higher latitudes move equatorward and are reinforced by upper-level wave patterns, they can generate episodes of low temperature over regions that are usually warmer. Because the thermal inertia of land is small compared with that of the ocean, these anomalies can develop quickly and move across the supercontinent, sometimes interacting with monsoon circulation and storm tracks to create complex sequences of weather events. The seasonal cycle also influences storm intensity over the surrounding superocean. In warm seasons, higher sea surface temperatures in some regions of Panthalassa can support the formation of tropical cyclones, which are rotating storm systems with strong winds and heavy rain that draw energy from warm ocean water. When such storms move toward the coast of Pangea, they can deliver intense rainfall and high winds to coastal and near-coastal areas, contributing to erosion flooding and rapid sediment transport. The frequency tracks and typical landfall points of these storms depend on the patterns of sea surface temperature, vertical wind shear, and large-scale circulation, all of which are shaped by the configuration of the supercontinent and the structure of the global climate system at the time. Over long intervals, the combined effect of seasonal monsoon cycles, mid-latitude storms, heat waves, cold outbreaks, and tropical cyclones defines the range of environmental conditions that organisms and landscapes experience along the margins of Pangea. These processes control when and where water is available, how often extreme events occur, and how energy and materials move between land, sea, and atmosphere across the annual cycle in the supercontinental world. During the time when Pangea is assembled mountain belts and high plateaus play a central role in shaping regional climates across the supercontinent by steering winds forcing air to rise and cool, and creating sharp contrasts in rainfall between their windward and leeward sides. Many of these mountains record earlier collisions that helped build Pangea, such as the long ranges that run through what will later become eastern North America and Western Europe, the belts that mark the joining of Siberian and European blocks in the region of the future Urals, and the uplands that trace sutures between southern continental fragments. These ranges consist of thickened crust that has been faulted and uplifted over millions of years as plates converged. In cross-section, the crust beneath them is thicker than beneath surrounding lowlands, and this extra thickness supports higher elevations through isostasy, which is the gravitational balance between dense mantle material and lighter crust. Overlying these deep structures are complex arrays of ridges, valleys, and plateaus, where erosion has sculpted earlier uplifted rocks into a range of landforms. Some sectors preserve high-standing peaks and steep slopes, while others are more subdued due to long periods of weathering and denudation. Even modest uplifts, however, can influence atmospheric flow when they extend for hundreds to thousands of kilometers along the path of prevailing winds. As moist air moves inland from Panthalassa or from Tethyan seas and encounters these mountain belts, it is forced upward along windward slopes. As the air ascends, it expands and cools. Cooling reduces its capacity to hold water vapor, and at some point condensation begins forming clouds and then precipitation. This process, known as orographic uplift, enhances rainfall on the upwind side of the range. Over long intervals, such uplift-driven rainfall can support dense vegetation, more deeply developed soils, and active river systems that carry water and sediment down from the slopes into fallen basins or coastal plains. Floodplains, alluvial fans, and deltas associated with these rivers record repeated cycles of deposition incision and shifting channels as climate and tectonic conditions change. On the leeward side of the same mountains, descending air behaves differently. After losing moisture on the windward side, the air crests the range and begins to flow down slope. As it descends, it compresses and warms, increasing its capacity to hold water vapor and reducing relative humidity. Clouds tend to dissipate in this warming air, and precipitation becomes much less frequent. The result is the formation of a rain shadow region, a leeward zone of reduced rainfall that can extend for long distances into the interior of the supercontinent. In Pangea, this effect likely reinforces the development of already dry interior belts. For example, where long mountain chains run approximately parallel to the coast and intercept moist winds coming from Panthalassa or Tethyan seas, the upwind slopes and adjacent lowlands may be relatively wet, while the downwind interior areas receive little moisture and support deserts or semi-deserts. In this way, mountain belts act as large-scale barriers that amplify the contrast between coastal or near-coastal wet climates and interior arid climates. The exact configuration of these rain shadows depends on the orientation of ranges relative to prevailing winds, the height and continuity of the topography, and the seasonal migration of wind belts associated with the monsoon cycle and global circulation. In some seasons, winds may strike a range more directly enhancing orographic precipitation, while in other seasons winds approach at a different angle or from a different source region, altering the distribution of rainfall. Over geological timescales, ongoing uplift and erosion adjust the height and width of mountain belts. Episodes of renewed tectonic activity can cause additional crustal thickening, faulting, or folding, raising new peaks, or rejuvenating existing topography, while erosion by rivers' mass, wasting, and glacial processes in cooler high-altitude regions works to smooth slopes, cut valleys, and lower summit heights. During cooler intervals, snow may accumulate at higher elevations during winter, and in some cases small or regional ice fields, and valley glaciers could form especially in high-latitude ranges or on lofty plateaus. These ice masses, if present, would further shape the landscape by carving cirques and U-shaped valleys and delivering glacial sediments downslope, although in the generally warm states that characterize much of the Pangean interval, such glaciation is likely limited in extent and duration. Whether carved by ice or running water, mountain valleys collect runoff and funnel it into river systems that can extend from uplifted interiors to distant margins. These rivers transport large volumes of sediment eroded from the ranges, including coarse gravels in proximal areas and finer sands and muds downstream. In fallen basins adjacent to major origins, the weight of accumulating sediment adds to tectonic subsidence, creating broad depressions that can host thick successions of fluvial deltic and shallow marine deposits. These basins often become important sites for the storage of organic material and for the development of diverse ecosystems during periods when climate and water availability permit. In drier climates, some fallen basins may instead fill with alluvial fan deposits, player lake sediments and evaporates, reflecting the interplay between uplift-driven sediment supply and rain-shadow-induced moisture limitation. Mountain belts also influence local and regional temperature patterns. Higher elevations experience lower mean temperatures than surrounding lowlands, because air temperature decreases with altitude in the troposphere. This lapse rate leads to cooler conditions on plateaus and peaks, even when the broader region is warm. As a result, mountain regions can serve as refuges for plant and animal communities that are adapted to cooler or more humid environments, while adjacent lowlands may be dominated by vegetation suited to higher temperatures and drier conditions. Elevation gradients create bands of different vegetation types and soil development on a single mountain flank. For instance, lower slopes may host woodland or shrubland, where precipitation and temperature are moderate mid-slopes, may support denser forest or more moisture-demanding plant communities if rainfall is high, and upper slopes may bear sparse alpine-like vegetation or bare rock, where cold wind and steep gradients limit soil formation and plant growth. These altitudinal zonations in turn affect runoff infiltration and the partitioning of precipitation into surface and subsurface flows. The interaction of mountain belts with the atmosphere can also generate local wind systems such as mountain valley breezes and downslope windstorms. During the day, slopes warmed by the sun can induce upslope winds that transport air and moisture toward higher altitudes, enhancing convective cloud formation over ranges, while at night, cooling of the surface can drive denser air downslope into valleys. In some cases, strong pressure differences across a range can produce fast downslope winds on the leeward side that are warm and dry, reinforcing the aridity of rain shadow regions and occasionally causing episodes of rapid drying and heating at the surface. Over millions of years, the position and shape of mountain belts on Pangea change as plates continue to move and internal forces reconfigure the crust. New collisional zones may initiate in some sectors, while earlier ranges become more eroded and subdued. These long-term adjustments change where rain shadows fall, how monsoon flows interact with topography, and which basins receive the most sediment and water. As the supercontinent ages, local uplift and subsidence events can create new pathways for atmospheric flow and new patterns of drainage, gradually reshaping the map of wet and dry regions. Throughout the Pangean interval, however, the consistent role of mountains is to act as large-scale obstacles in the path of winds, to concentrate precipitation on windward slopes and to cast broad rain shadows that help sustain extensive arid belts. By modulating the distribution of moisture and temperature across the joined landmass, these uplifts become key controls on the spatial pattern of climates and habitats, linking deep tectonic processes in the crust with surface environments through the physics of airflow and precipitation. During the time when Pangea spans much of one hemisphere, parts of the supercontinent and its surrounding margins host volcanism on a scale that differs from more familiar isolated eruptions, because in some regions magma rises through the crust in volumes large enough to form what geologists call large igneous provinces. These provinces consist mainly of thick sequences of basaltic lava and related intrusive bodies that spread across and into the crust over intervals of hundreds of thousands to several million years. Instead of single steep volcanoes, many of these events build wide plateaus made of stacked lava flows that travel long distances from fissures and vents. Each flow is fed by fractures that open as magma from the mantle ascends, and over repeated episodes the flows accumulate into layers hundreds to thousands of meters thick. In the late Permian and early Triassic, for example, the region that will later be known as Siberia contains one of the most extensive of these volcanic systems, and other sectors of Pangea and its future fragments also host widespread basaltic outpourings and intrusions around key intervals of tectonic and magmatic change. In each case, the crucial point is that the rate of magma production and the total volume erupted or intruded are large enough that the effects extend far beyond the immediate vicinity of vents. As basaltic magma rises, it carries dissolved gases that come out of solution when pressure decreases near the surface. These gases include water vapor, carbon dioxide, sulfur species such as sulfur dioxide and hydrogen sulfide halogen, compounds containing chlorine and fluorine, and small amounts of other components. When lava reaches the surface and degasses, or when magma stalls in shallow chambers and releases volatiles into surrounding rocks, and the overlying atmosphere, these gases enter the air and interact with existing atmospheric constituents. Carbon dioxide is long-lived and distributes widely, mixing throughout the troposphere and eventually the stratosphere, where it acts as a greenhouse gas that reduces the efficiency with which Earth can radiate heat back to space. Water vapor released by eruptions typically has a shorter local effect because it condenses and joins the active hydrologic cycle, but it can still influence cloud formation near volcanic plumes. Sulfur dioxide plays a distinct role because it can be converted in the atmosphere into sulfate aerosols, which are tiny droplets or particles containing sulfuric acid and related compounds. These aerosols can persist for months to years in the stratosphere and can reflect a fraction of incoming solar radiation back to space. The combined effect of repeated eruptions in a large igneous province is not a single short-lived climate pulse, but a pattern in which episodes of intense effusion and degassing recur over long intervals. During times of strong sulfur release, increased stratospheric aerosol loading can lower surface temperatures, especially over continents, and reduce the amount of sunlight reaching the ground. At the same time, the long-term addition of carbon dioxide and other greenhouse gases tends to warm the climate system on multi-thousand to million-year timescales by increasing downward infrared radiation. This means that the climatic response to large-scale volcanism is complex and depends on the relative balance and timing of short-term cooling from sulfur aerosols and longer-term warming from greenhouse gas buildup. In the Pangean world, where baseline conditions are already warm and continental interiors experience substantial heat and dryness, additional greenhouse forcing can push some regions toward higher average temperatures and more intense heat extremes, even as transient aerosol events may introduce cooler intervals or stronger temperature contrasts between land and ocean. Another important aspect of large volcanic systems in and around Pangea is the interaction between rising magma and pre-existing sedimentary rocks in the crust. When basaltic sills and dikes intrude into layers rich in organic matter, such as coal seams or organic-bearing shales, the heat from the intrusions can drive contact metamorphism and thermal breakdown of the organic material. This process releases additional gases including carbon dioxide and methane, which can escape along fractures to the atmosphere. Similarly, intrusion into carbonate rocks and some evaporate deposits can liberate carbon dioxide and halogen-rich gases. In this way, the total volatile output associated with a large igneous province may be significantly higher than what is directly dissolved in the magma itself, because the heated country rock becomes a secondary source of greenhouse and chemically active gases. The composition and thickness of the sedimentary pile into which magma intrudes therefore play a major role in determining the type and amount of volatiles released. The vertical distribution of volcanic emissions within the atmosphere also matters. Explosive phases of activity, especially when magma interacts with external water, or when gas pressure within the magma is high, can inject ash and gases directly into the stratosphere. Their aerosols and gases can spread over very wide areas, encircling much of the globe within weeks to months. In contrast, more effusive, less explosive episodes may release most of their gases into the lower troposphere, where they are removed more quickly by weather systems and precipitation. Both modes are present to varying degrees during the lifespan of a large igneous province. Stratospheric injections are particularly effective at altering radiative balance and upper-level chemistry, while tropospheric emissions have stronger immediate impacts on air quality, cloud microphysics, and near-surface environments in downwind regions. Sulfur dioxide and halogen emissions from sustained volcanism can also affect atmospheric chemistry beyond their radiative effects. In the presence of sunlight and other reactive species, these emissions can lead to the formation of compounds that interact with ozone, especially in the stratosphere. Changes in ozone concentration modify the amount of ultraviolet radiation that reaches the surface, and also influence temperature structure in the upper atmosphere, because ozone absorbs ultraviolet light and converts it into heat. The precise extent of ozone perturbation during Pangean large igneous province activity remains uncertain and likely varies with the scale and timing of eruptions, but chemical modelling and observations of modern eruptions show that strong injections of halogen and sulfur species can at least temporarily reduce ozone levels locally or regionally. If such reductions extend over broader areas or recur frequently, they can alter the balance of radiation and chemistry in ways that contribute to environmental stress. On land near major eruptive centres, lava flows, ash falls, and gas-rich plumes transform local landscapes directly. Lava can cover pre-existing soils, wetlands, or forests with basaltic rock, creating new surfaces that slowly weather and develop new soils over long periods. Pyroclastic deposits from more explosive phases can bury existing topography under layers of fragmented volcanic material. Gases such as sulfur dioxide and hydrogen sulfide can lead to the formation of acid rain when they dissolve in atmospheric moisture and are oxidized, lowering the pH of precipitation that falls on nearby ecosystems and on downwind regions. Acidic rainfall can enhance chemical weathering of rocks and soils and can stress vegetation and freshwater systems, especially where buffering capacity is low. Ash and aerosols can reduce the amount of sunlight reaching surface waters, affecting photosynthesis in terrestrial and aquatic primary producers. In the ocean surrounding Pangea, volcanic gases released into the atmosphere eventually dissolve into surface waters or are carried by rain and river runoff. Carbon dioxide taken up by the ocean increases the concentration of dissolved inorganic carbon and can lower seawater pH, a process known as ocean acidification. The magnitude and rate of this acidification depend on the speed and total amount of carbon input relative to the capacity of the ocean to absorb and chemically buffer it through carbonate equilibria and interaction with sediments. Persistent or rapid inputs can outpace these buffering processes, causing more sustained decreases in pH that influence carbonate saturation states. Sulfur species and associated aerosols can deposit onto the ocean surface, adding sulfate and altering the light environment in the upper water column. In some regions, volcanic ash supplies nutrients such as iron, which can stimulate phytoplankton growth, while in others, the combination of reduced light and chemical changes may limit primary production. Over the full duration of a large igneous province event in the Pangean interval, repeated pulses of magma emplacement, lava effusion, and volatile release mean that the atmosphere and oceans experience not a single disturbance, but a series of overlapping perturbations. Between eruptive pulses, some aspects of the climate system may move toward new quasi-stable states, defined by elevated greenhouse gas levels, modified circulation patterns, and altered chemistry. During pulses, short-term extremes associated with aerosol-loading acid rain and local air quality changes are superimposed on this longer-term background. The capacity of Earth's systems to absorb, redistribute, and gradually remove these volcanic inputs depends on processes such as silicate weathering on land, carbonate precipitation, and dissolution in the ocean, and burial of organic carbon. In the Pangean world, where interior aridity can limit some forms of chemical weathering, and where the configuration of oceans reduces the area of shallow continental seas, the pathways and rates of these feedbacks differ from those in later continental arrangements. As a result, the large igneous provinces that operate during this interval represent powerful long-term sources of heat trapping and chemically active gases that reshape the physical and chemical environment within which climate oceans and ecosystems must operate. In the oceans that surround and fringe Pangea, the circulation of water, the exchange of gases with the atmosphere, and the cycling of nutrients work together to set the chemical state of the seas, including how much oxygen is available at different depths. At the surface, where water is in direct contact with the airwaves and turbulence continuously mix gases into the upper ocean, oxygen dissolves into seawater in amounts that depend on temperature, salinity, and atmospheric concentration. Cooler surface waters can hold more dissolved oxygen than warmer waters, and fresher water can hold slightly more than saltier water. Photosynthesis by marine phytoplankton. In the sunlit upper layer also produces oxygen, locally adding to the dissolved pool while it removes carbon dioxide and nutrients. When these organisms respire or are consumed by other organisms, they use oxygen again, and when they die, their remains sink and decay, consuming oxygen at depth. This vertical separation between oxygen production near the surface and oxygen consumption in deeper waters is a normal feature of marine systems. In the Pangean world, however, several factors combine in some times and places to deepen the difference between oxygen-rich and oxygen-poor zones. One key factor is the tendency for warming and changes in salinity to increase the stability of stratification, which is the layering of water masses of different densities. As surface waters warm, they become less dense and more buoyant relative to cooler waters below. If evaporation in warm subtropical belts increases surface salinity, it can act in the opposite direction, making surface water denser, but the balance between temperature and salinity effects varies from region to region. Where warming dominates the density, contrast between surface and deeper waters grows stronger, and vertical mixing becomes more difficult. In such stratified conditions, the renewal of oxygen in underlying layers slows, because less surface water is able to sink, and less deep water is brought back up in direct exchange. At the same time, the supply of organic matter to depth may increase if productivity in the surface ocean is high, or if nutrient delivery to coastal seas is enhanced by stronger weathering and runoff from land. Weathering of rocks on Pangea and transport of dissolved nutrients by rivers into marginal seas and coastal zones provide phosphorus, nitrogen, and trace metals that fuel phytoplankton growth. Volcanic ash and dust from interior deserts can also contribute nutrients such as iron when deposited on the ocean surface. In regions where these inputs are significant, surface waters can support dense blooms of plankton. When these organisms die and sink, the microbial decomposition of their remains consumes oxygen in the water column and at the seabed. If stratification limits the supply of new oxygen to these depths, oxygen levels can fall progressively, creating oxygen minimum zones that are more intense and extensive than in less stratified states. In extreme cases near bottom and mid-depth, waters can become anoxic, meaning they contain little or no dissolved oxygen. Under these conditions, microbial processes that do not require oxygen become more important. Some microbes use nitrate sulfate or other compounds as electron acceptors in their metabolic pathways. In waters where sulfate reduction dominates, hydrogen sulfide can accumulate. When this hydrogen sulfide-rich water sits beneath an oxygenated upper layer, a chemical and biological interface develops where sulfide is oxidized back to sulfate, often with the help of specialized microbes. If hydrogen sulfide-bearing waters rise toward the surface or expand into shelf areas, they can create euxinic conditions in which water is both anoxic and sulfidic through a thicker vertical zone. The occurrence and extent of such conditions during the late Permian and early Triassic are subjects of active research. Multiple lines of evidence, including isotopic signatures, the presence of certain mineral phases and patterns in fossil preservation, suggest that in some basins and time intervals, large parts of the water column experience low oxygen or euxinic states, while in others well-oxygenated conditions persisted. These differences likely reflect a combination of local basin geometry rates, of nutrient input, water column stratification, and the strength and pattern of deep circulation. The geometry of Panthalassa and its connected seas influences where low oxygen zones can develop. Broad, deep open ocean regions with strong overturning circulation may retain relatively better oxygenation in their interior, while more restricted basins and continental margin settings with limited deep water renewal can be more prone to oxygen depletion. Narrow connections between interior seas and the main superocean can limit the exchange of deep water, allowing oxygen consumption by decaying organic matter to outpace resupply, if freshwater input from rivers or high surface productivity strengthens surface stratification. In such basins, the tendency toward anoxia increases. Shallow shelves are particularly sensitive because they sit at the interface between land-derived nutrient supplies and open ocean circulation. When sea level is high enough to flood broad continental margins, these areas can host productive ecosystems that act as strong sinks for oxygen below the surface mixed layer. In the Pangean configuration, however, the total area of shallow epicontinental seas is smaller than in times with more fragmented continents. So much of the shelf environment is concentrated along long narrow margins and in specific interior seas such as the Tethys region. This arrangement may focus zones of high productivity and oxygen demand into particular belts, while leaving broader deep ocean areas with different chemical states. The accumulation of organic-rich sediments in low oxygen settings has another effect on seawater chemistry over longer timescales, because when organic carbon is buried rather than fully oxidized, it removes carbon from the active carbon dioxide reservoir. However, if warming and volcanically driven carbon dioxide input are large and rapid, burial of organic carbon may not fully counteract the addition of greenhouse gases, and the overall tendency toward warmer conditions and altered circulation can persist. Meanwhile, in the short to intermediate term, water column oxygen depletion affects cycling of other elements. Under anoxic conditions, reduced forms of iron and manganese become more soluble and can be mobilized from sediments into the water column. When these reduced species encounter more oxidizing layers above, they can precipitate as oxides and hydroxides, forming distinct bands and nodules that later become part of the rock record. Phosphorus cycling is also sensitive to redox conditions because under low oxygen, phosphorus bound to iron oxides can be released back into the water, potentially fueling further productivity and reinforcing the feedback between nutrient availability and oxygen demand. Trace metals such as molybdenum, uranium, and vanadium likewise respond to redox changes and are preferentially incorporated into sediments under anoxic or euxinic conditions leaving chemical signatures that are used to reconstruct past oxygen levels. The shift toward more extensive low oxygen zones and possible expansion of euxinic conditions in some Pangean basins does not necessarily occur uniformly or simultaneously across the global ocean. Instead, it likely happens in patches and phases, with some regions entering and exiting low oxygen states at different times, influenced by local circulation, climate, and tectonic settings. There may be intervals when deep water formation in certain high-latitude regions strengthens, bringing more oxygenated water into the interior and partly reversing oxygen depletion, followed by times when warming and freshening or changes in wind patterns reduce overturning and allow anoxia to expand again. This dynamic behavior adds complexity to the environmental backdrop of the late Permian and early Triassic seas. For organisms living in these oceans, the vertical and horizontal distribution of oxygen shapes the habitats available for active swimmers, benthic communities, and planktonic life. Zones of well-oxygenated water can still support diverse communities in some regions, while wherever low oxygen or euxinia encroach on continental shelves and upper slopes, stress increases for many groups, especially those that require well-oxygenated conditions and cannot easily migrate. Even without entering into specific extinction patterns, it is clear that the gradual and sometimes rapid changes in ocean stratification chemistry and oxygen availability during the Pangean interval define a marine environment where the margin between tolerable and stressful conditions moves through time and space, setting a critical context for any subsequent biological responses. Across the time when Pangea dominates Earth's surface, the combined influence of changing oceans, climate and volcanic activity is expressed in the living world as a series of disruptions that in some intervals build toward broad patterns of ecosystem collapse on land and in the sea. In marine settings, one of the most striking large-scale patterns seen in the rock record of the late Permian and earliest Triassic is the decline and disappearance of long-established reef-building communities. Before the crisis, reefs are constructed by diverse assemblages of organisms including calcareous sponges, rugose and tabulate corals, and various skeletal algae which together create rigid frameworks that rise above the seafloor in warm, shallow waters along continental margins and around platforms. These structures host complex communities of invertebrates and fishes that occupy many ecological roles. As environmental stress increases, these framework building groups show signs of reduced abundance and diversity. In many sections, the final late Permian reef horizons are followed by intervals in which only low-relief carbonate mounds or thin skeletal layers remain, and in the earliest Triassic true reef frameworks are rare or absent for a significant span of time. Instead, microbialites, which are structures formed by microbial communities that trap and bind sediment or precipitate carbonate, often dominate shallow substrates. This replacement suggests that the conditions that once allowed complex skeletal reef builders to flourish become unfavorable, and that simpler, more tolerant microbial communities move into the available space. Beyond reefs, open shelf and slope communities also show characteristic shifts. Late Permian faunas in many regions include a wide variety of brachiopods, bivalves, gastropods, crinoids, ammonoids, and other invertebrates arranged in depth-related assemblages. As stress accumulates, these assemblages thin and change composition. In some basins, fossil records show that certain groups disappear earlier or more completely than others. Many brachiopod clades, especially those with narrow environmental tolerances or specialized feeding modes, decline sharply or vanish, while some bivalves, especially those capable of living in more disturbed or low oxygen settings, persist or expand. Ammonoids, which are free-swimming cephalopods, experience rapid fluctuations, with some clades showing short-lived blooms followed by abrupt declines. The resulting early Triassic faunas are often dominated by a smaller number of opportunistic taxa that can tolerate variable or stressful conditions, While many formerly diverse lineages are absent, vertical gradients in community structure also change. In well-oxygenated systems, benthic communities show clear variation with depth, reflecting differences in light substrate and food supply. When low oxygen conditions expand on continental shelves and upper slopes, fossil assemblages from those depths often shift toward low-diversity stress-tolerant forms, or show evidence of reduced bioturbation, such as finely laminated sediments, with few signs of burrowing or disturbance by benthic animals. In extreme cases, macrofossils become sparse or absent over intervals, suggesting substantial loss or displacement of community types at particular depths. These patterns indicate that as water column structure and chemistry change the habitable space for many marine organisms, contracts both vertically and horizontally, and ecological interactions reorganize around a smaller set of surviving or opportunistic species. On-land ecosystems linked to Pangea's climate also undergo large changes. Late Permian floras in many regions include extensive forests with seed ferns, conifers, and other gymnosperms forming closed canopies in wetter belts, and more open woodlands and shrublands in drier zones. In the sedimentary record, this vegetation appears as abundant plant fossils, coal seams formed from accumulated plant matter in wetland settings, and soils with features consistent with prolonged biological activity in root systems. As environmental conditions shift, evidence for widespread forest cover in some regions declines. Coal formation becomes less common, or ceases in many basins, suggesting that the wet, stable conditions needed to accumulate thick peat deposits become rarer. Plant assemblages in some mid-latitude and high-latitude regions show a reduction in diversity and a shift toward more stress-tolerant types that can withstand greater variability in moisture or temperature. Leaf and wood fossils indicate replacement of complex multi-layered forests by more open, low-stature vegetation or by assemblages dominated by a few hardy taxa. In some intervals, there is an apparent increase in the abundance of spore-producing plants and pioneer species that are well suited to colonizing disturbed ground, consistent with more frequent disturbance or more unstable climate regimes. Soils developed under these changing vegetation patterns record alterations in hydrology, organic matter input, and weathering intensity. Indicators of prolonged, well-drained, biologically active soils, such as thick profiles with strong horizon development and abundant root traces, can give way to thinner, more weakly developed horizons with higher contents of soluble salts or carbonates, reflecting drier conditions, more irregular moisture supply, or greater erosion. In some regions, increased sediment yields from catchments lead to more rapid burial of soils and plant communities, by fluvial or volcanic clastic deposits interrupting pedogenesis and leaving a record of unstable landscapes. Charcoal fragments in these sediments record recurrent wildfires, and in some sequences there is evidence that fire becomes more common or widespread, altering plant community composition and structure. Fire forest dieback and soil erosion together connect changes in vegetation with the delivery of sediment and nutrients to rivers and coastal seas, linking terrestrial and marine collapse patterns. Terrestrial vertebrate faunas across Pangea also reflect ecosystem stress and reorganization. Late Permian assemblages of land vertebrates include diverse therapsids, which are synapsids with both reptile-like and mammal-like traits, large herbivores and carnivores, and a variety of early reptiles. Trackways and body fossils show complex food webs with multiple predator and prey-size classes. In the record spanning the Permian-Triassic boundary, many of these therapsid lineages decline or disappear, and early Triassic assemblages in several basins are dominated by a smaller number of taxonomic groups, including some early archosaurs and other reptilian clades. Body size distributions shift toward medium and small forms, and ecological roles formerly occupied by large herbivores and apex predators may be held by different or fewer species. Some regions show evidence of pronounced faunal turnover, where pre-existing communities are replaced by new assemblages with different taxonomic and ecological composition, rather than simply reduced versions of earlier faunas. These shifts suggest both extinction and migration, as some lineages may retreat to refugia, while others expand into newly available niches. The temporal pattern of these changes is not a single instantaneous break everywhere. Stratigraphic records from different parts of Pangea and its margins reveal that ecological disruption unfolds over intervals that can include pulses of more rapid change. In some localities, indicators of stress appear before the main extinction horizon, such as reduced diversity in specific groups, changes in the growth patterns of certain organisms, or shifts in sedimentary features that reflect altered environmental conditions. In others, major breaks across boundary layers, sometimes marked by distinctive geochemical signals or changes in lithology, separate relatively richer pre-boundary assemblages from poorer or compositionally different post-boundary faunas and floras. Following these main breaks, additional fluctuations often occur with short episodes of partial recovery, followed by further setbacks. This pattern is especially evident in marine systems where post-extinction faunas may show brief increases in diversity or abundance, before being affected by renewed stress associated with continuing environmental instability. Spatially, the severity and timing of collapse vary. Some basins show strong evidence of prolonged anoxia and low diversity in marine ecosystems throughout the earliest Triassic, while others retain pockets of more diverse, better oxygenated communities. On land, certain regions show more continuous records of vegetation and vertebrate turnover, whereas others are dominated by erosion surfaces or unconformities where parts of the record are missing. High-latitude areas may display different sequences than low-latitude interiors or coastal belts, reflecting differences in climate-forcing hydrology and proximity to active volcanic or tectonic centers. This variability indicates that while the overall pattern is one of major global disruption, local and regional histories are shaped by the particular combinations of oceanographic, climatic, and geological factors acting in each area. Across both realms, a common feature of collapse is simplification. Food webs that formerly contained many interacting species and functional groups contract to systems dominated by fewer, often more generalist or tolerant taxa. In marine settings, this simplification appears as low-diversity faunas dominated by a small number of invertebrates and plankton types, replacement of complex reef frameworks by microbial structures, and suppression of bioturbation in sediments. On land, it appears as reductions in forest complexity, dominance of disturbance, adapted plants loss, or reduction of some large-bodied vertebrate forms and faunas with fewer taxonomic and ecological categories. These simplified systems can remain in place for extended intervals, suggesting that environmental conditions stay within ranges that prevent rapid re-establishment of pre-existing complexity. Only after these phases, as conditions begin to change again, do more diverse and structured ecosystems gradually reappear in many regions, but that later recovery belongs to another stage in the Pangean story. Here, the focus rests on the observation that during a particular part of the Pangean interval, patterns in rocks, fossils and sediments together indicate widespread and often severe disruption of both marine and terrestrial ecosystems, expressed as sequential losses, turnovers, and reorganizations across the supercontinent and its surrounding seas. When the patterns of environmental change and ecosystem disruption during the late Permian and earliest Triassic are viewed together, they point toward a combination of physical and chemical stresses rather than a single simple cause, and the task becomes to understand how these stresses interact to produce such high extinction severity, while also recognizing where the evidence still leaves room for uncertainty. One major line of interpretation links large igneous province volcanism with long-term greenhouse gas accumulation and progressive warming of the climate system. Elevated carbon dioxide from sustained magmatic and contact metamorphic degassing increases the radiative forcing of the atmosphere, and over tens to hundreds of thousands of years this forcing can raise global mean temperatures by several degrees Celsius or more. In a world that already has broad warm belts and extensive continental interiors, additional warming can push some regions into conditions with very high seasonal and daily maximum temperatures. For many land organisms, especially large active vertebrates and plants with particular temperature and moisture requirements, such thermal stress can reduce viable habitat ranges, increase metabolic and water loss demands, and narrow the windows of the day or year when activity is possible. In marine settings, increased surface temperatures not only stress organisms directly, but also amplify stratification, as warmer, less dense surface waters resist mixing with cooler deep waters. This enhanced stratification slows the renewal of oxygen at depth and contributes to the expansion of oxygen minimum zones. As productivity and organic matter export continue decay in deeper waters, consumes the available oxygen. In some basins, the result is widespread anoxia, and in more extreme cases, euxemia, where hydrogen sulfide accumulates. For organisms that require well-oxygenated water, including many benthic invertebrates and active nectonic animals encroaching, anoxia effectively removes large parts of the water column and seafloor from habitable space. Even groups that can tolerate reduced oxygen may encounter limits as low oxygen zones become thicker or extend onto shelves. The chemical byproducts of low oxygen conditions, including hydrogen sulfide and altered nutrient regimes, further modify habitats and can favour microbial groups that reinforce the stressed state. At the same time, carbon dioxide released to the atmosphere equilibrates with seawater and shifts the balance of carbonate chemistry, lowering pH and altering saturation states for calcium carbonate minerals. This ocean acidification affects organisms that build shells or skeletons from carbonate, especially those with high magnesium calcite or aragonite, which are more soluble forms. Difficulties in secreting or maintaining shells can reduce growth rates, weaken structures, or bias success toward taxa with different mineralogies or life strategies. Experimental and comparative data from modern systems show that many marine calcifiers are sensitive to relatively modest pH changes, but translating these sensitivities to ancient taxa and conditions requires caution, so the precise contribution of acidification to extinction remains an active area of investigation. It is likely, however, that acidification at least adds to the stress of warming and oxygen loss in shallow marine environments, particularly for reef builders and plankton with carbonate tests. On land, warming interacts with changing precipitation patterns, stronger monsoon contrasts in some regions, and persistent aridity in others. Where forests previously stabilized soils and moderated local climates, increased temperature shifting rainfall, and more frequent droughts can weaken plant communities. Drought-stressed vegetation is more flammable, and combined with lightning and possibly increased frequency of dry storms, this condition can lead to more widespread wildfires. Charcoal in sediments and burnt horizons in soils from the relevant interval suggest recurrent fire activity in many basins. Fire removes biomass, exposes soils, and contributes to pulses of erosion and sediment transport. As soils thin or are stripped from slopes, their capacity to hold water and nutrients declines, making it more difficult for complex plant communities to re-establish and reinforcing a move toward more open disturbance-adapted vegetation. Loss of root systems and organic rich soil horizons reduces the ability of landscapes to buffer changes in hydrology, and rivers can carry larger loads of sediment and dissolved material to coastal seas, where they influence marine chemistry and productivity. This linkage between terrestrial degradation and marine stress strengthens feedbacks between spheres. Another potential factor discussed in connection with the severity of the crisis is change in atmospheric oxygen and possibly ozone. Geological and geochemical evidence suggests that atmospheric oxygen, after reaching high levels earlier in the late Paleozoic, may decline across the Permian-Triassic interval. Lower oxygen in the air would reduce the partial pressure gradient driving oxygen uptake in animal respiratory systems, and could constrain maximum body size activity levels and altitudinal ranges. However, the magnitude, timing, and direct biological impact of these oxygen changes are still debated, and available proxies are indirect, so the extent to which atmospheric oxygen decline contributes specifically to extinction versus longer-term evolutionary trends remains uncertain. For ozone, the concern is that large volcanic emissions of halogens and nitrogen oxides, combined with altered atmospheric circulation and temperature structures, might weaken the protective ozone layer. Models and modern analogues indicate that strong volcanic input can damage ozone locally and regionally, increasing ultraviolet radiation at the surface, but the global extent, persistence, and biological consequences of such changes during the Pangean events are not tightly constrained. Some proposed scenarios involve episodes where hydrogen sulfide from oceanic waters reaches the atmosphere and also interacts with ozone chemistry, but the evidence for large-scale sustained release of hydrogen sulfide to the air and its role as a direct kill mechanism remains incomplete and is the subject of continuing research. The possible involvement of other triggers such as large impacts has been examined, but at present no impact structure of the appropriate age, size and characteristics has achieved broad acceptance as a primary driver of the late Permian crisis. This does not entirely rule out additional contributions from events not yet recognized in the record, but the weight of current evidence tends to favor a volcanically driven scenario, with climate and ocean changes as main intermediaries rather than a single brief catastrophic impact. An important open question concerns the pacing and structure of the environmental and biological changes. Some records point to a relatively sharp main extinction pulse, occurring over a geologically short interval, perhaps on the order of tens of thousands of years or less, superimposed on longer background trends. Others suggest multiple phases of elevated extinction or stress separated by partial recoveries or plateaus. Variations in sedimentation rate, completeness of the record, and dating precision complicate efforts to resolve these patterns, and different basins may preserve different segments or expressions of the overall history. This means that estimates of extinction duration and the exact sequence of environmental events remain approximate and can differ between studies. Closely related to pacing is the question of thresholds and tipping behaviours. It is not yet fully clear how gradual increases in carbon dioxide temperature and ocean stratification translate into more abrupt biological responses. One possibility is that as conditions approach certain thresholds relatively small, additional changes can cause major reorganizations, such as rapid expansion of anoxic zones or failure of key ecosystem components like reef builders or dominant tree species. Identifying these thresholds in the geological record is challenging, because proxy signals often average conditions over substantial time windows, and cause and effect can be difficult to separate when many processes operate simultaneously. There is also ongoing work to clarify why some groups suffer extreme losses, while others persist or even expand. Differences in physiology, such as tolerance to high temperature, low oxygen, or low pH, likely play roles, as do life history traits, reproductive strategies, and ecological flexibility. For example, taxa able to exploit disturbed habitats tolerate a wide range of conditions, or disperse across large distances may have better chances of survival and diversification under changing environments. However, detailed trait-based analyses are still developing, and in many fossil groups, key physiological details are inferred indirectly. As a result, assigning relative weight to different stresses in explaining taxon-specific fates remains partly speculative. Finally, the contribution of feedback mechanisms that either damp or amplify changes is an area of active inquiry. Silicate weathering on land, for instance, responds to temperature and precipitation, and over long periods can draw down atmospheric carbon dioxide, acting as a negative feedback on warming. Yet during intervals of severe aridity or widespread soil loss, the efficiency of this feedback may be reduced. In the ocean burial of organic carbon and carbonate, changes in overturning circulation and shifts in nutrient cycling can all influence how quickly the system responds to perturbations and whether it moves toward new steady states or experiences long oscillatory adjustments. The relative strengths and timescales of these feedbacks during the Pangean events are not fully constrained, making it difficult to reconstruct in detail how the Earth system transitions from pre-crisis to peak crisis conditions. Taken together, current understanding supports a view in which large-scale volcanic activity introduces substantial amounts of greenhouse and other gases into the atmosphere, driving global warming, ocean stratification, acidification, and chemical changes, which in turn interact with land surface processes, wildfires, and biogeochemical cycles to stress ecosystems. At the same time, the rock and fossil record also makes clear that this picture is incomplete in its details. Key questions remain about precise rates of change, regional variations, the hierarchy of causal pathways, and the reasons for differences in vulnerability among taxa and environments. The study of these mechanisms therefore continues to refine both the physical and biological narratives that describe how a world dominated by a single supercontinent and superocean experiences one of the most severe known losses of life in Earth's history. After the peak of disruption near the end of the Permian, the world around Pangea enters an interval in which environmental conditions remain stressed, but begin to allow partial and slowly expanding recovery of ecosystems on land and in the sea. In marine settings, many shelf regions that once supported diverse reef and benthic communities now host low-relief seafloors where sediment accumulation, microbial activity, and a limited set of invertebrates together define the new baseline. Microbialites remain common in shallow waters, forming layered structures that grow on hard substrates or within loose sediment. These microbial frameworks do not reach the size or structural complexity of earlier reefs, but they provide some three-dimensional relief and surface area in otherwise smooth environments. Small bivalves, gastropods, and a few other invertebrates occupy the surfaces and cavities of these structures, grazing on microbial films or feeding on suspended particles. Trace fossils in some of these sediments show that simple burrowing and crawling activity returns, though the density and diversity of such traces remain lower than in pre-crisis communities for extended intervals. In places where oxygenated water masses persist or gradually reoccupy parts of the water column, benthic communities begin to re-establish beyond the most tolerant forms. Thin layers of bioturbated sediment appear between more laminated intervals, indicating that organisms capable of burrowing and mixing the upper seabed take advantage of episodes when bottom water conditions improve. However, repeated returns of low oxygen or chemically stressful states interrupt these advances and create a patchwork of recovery and setback across different basins and depths. Vertically, the water column continues to display strong gradients in many regions. Surface waters support phytoplankton that respond to available nutrients and light, and the basic processes of primary production, grazing and sinking organic matter continue. In some sectors, the composition of planktonic communities shifts toward groups better suited to variable conditions, including fluctuations in nutrients, temperature, and pH. Over time, new combinations of primary producers and zooplankton help shape the energy pathways that support higher trophic levels. Nectonic organisms such as ammonoids and early actinopterygian fishes, which survive the crisis in reduced form, diversify again in some basins, and the open water column above, slowly stabilizing shelves and slopes, sees a gradual increase in species richness. The pace of this increase is not uniform, and local successions continue to be influenced by episodes of stratification, anoxia and changes in nutrient supply, but on long time scales, the pattern is one of uneven yet overall expansion from very low-standing diversity to more complex pelagic systems. Along continental margins, sedimentary environments also evolve as climates and tectonics change. In some regions, thick successions of red beds evaporites, and fluvial deposits record persistent aridity and strong seasonality. But within these sequences, intervals appear where finer-grained lake and floodplain sediments indicate periods of somewhat wetter conditions. Lakes in interior and near coastal basins become important temporary refuges for both aquatic and terrestrial organisms, and their deposits preserve fossils of fish, invertebrates, and plants that exploit these habitats. The presence of diverse microfossil assemblages such as spores and pollen in some early Triassic lake and deltic sediments suggests that plant communities in nearby catchments begin to diversify again, even if large-scale forests remain rare or reduced in many areas. On land, the most immediate visible change after the collapse is often simplification, but within this simplified state, early recovery can be traced in the slow establishment of new plant and animal communities. In many mid-latitude regions of Pangea, early Triassic floras are dominated by a limited set of taxa, including opportunistic seed ferns and conifer-like plants that tolerate dry, unstable, or strongly seasonal conditions. These plants colonize floodplains, low-relief uplands, and disturbed surfaces left by erosion and volcanism. Over time, as soils begin to redevelop and hydrologic regimes become more predictable, in some areas these pioneer communities are joined by additional gymnosperms and other groups, which gradually introduce more structural variety into vegetation cover. Root traces in soils become more abundant and deeper, and the complexity of soil horizons increases, indicating that plant communities are occupying sites for longer periods and influencing water and nutrient cycling more strongly. In high latitude or more humid belts where temperature and moisture regimes are less extreme, forests may reassemble more quickly with a broader set of tree forms and understory plants. In contrast, central arid interiors and some subtropical sectors continue to host sparse vegetation for extended times, and the recovery in terms of biomass and diversity is slower. Nevertheless, even in these challenging climates, certain hardy shrubs, small trees, and ground cover plants establish stable populations in more favourable microsites, such as along river corridors in depressions where water collects intermittently or near springs. These patches act as local hubs of biological activity and can serve as sources for further colonization during intervals when conditions become slightly more benign. Terrestrial vertebrate faunas also show patterns of gradual reorganization and diversification within this changing landscape. Early in the recovery interval, many regions are dominated by a few clades that survived the extinction and are tolerant of the prevailing environmental stresses. Some of these survivors are medium-sized herbivores that can exploit the available plant resources in open, patchy vegetation, while others are carnivores or omnivores that feed on these herbivores and on smaller vertebrates and invertebrates. Over time, as plant communities diversify and stabilize in parts of Pangea, herbivore assemblages begin to differentiate. New lineages of archosaurs and other reptiles appear or expand, exploring different body sizes and feeding strategies in response to the emerging mosaic of habitats. Predatory guilds adjust as well, with changes in bodyworm locomotion and dentition, reflecting the shift from the pre-crisis faunas to new sets of dominant terrestrial predators. These changes occur on timescales of millions of years and vary from basin to basin, but overall the structure of terrestrial food webs slowly becomes more complex again, with more pathways for energy flow and more specialized ecological roles. Climate remains an important constraint throughout this recovery phase. Evidence from sediments, isotopes, and fossil assemblages suggests that much of the early Triassic is marked by high global temperatures, strong seasonality in some regions, and episodes of continued environmental instability. Under these conditions, ecosystems that gain diversity and complexity during relatively stable intervals can be set back by renewed pulses of climatic or oceanographic change, including shifts in precipitation patterns, renewed expansions of low oxygen conditions in the sea, or pulses of volcanic activity. As a result, recovery is not purely linear. Instead, trajectories often include minor reversals or plateaus. Some regions show successive assemblages that rise in diversity contract during stress intervals, and then rise again with each cycle, potentially building on the remnants of previous communities or on new colonists that arrive as dispersal routes open. One way to track the progression of recovery on land is through changes in sedimentary facies that reflect vegetation cover and runoff. In strongly degraded landscapes, high erosion rates and rapid sediment delivery produce coarse, thick, and laterally variable fluvial deposits. As plant cover returns and soils thicken, slopes become more stable, and sediment yields can decline. Rivers begin to develop more persistent channels with better defined floodplains, and fine-grained overbank deposits become more common. Within these floodplains, paleosols with mature features and abundant root traces develop, and the frequency of unconformities associated with erosional stripping decreases. These changes indicate a shift from highly unstable surfaces dominated by physical processes to landscapes where biological activity and soil development exert more control on geomorphic evolution. In turn, this stabilizing trend supports further diversification of terrestrial communities by providing more reliable habitats and resources. In marine settings, comparable signals appear in the form of changes in carbonate platform architecture, patterns of bioturbation, and the return of more complex skeletal assemblages. Carbonate platforms that were reduced to thin or irregular microbial structures during the crisis begin to show thicker accumulations with contributions from various skeletal organisms. Bioturbation intensity increases, and the range of trace fossil types expands, indicating the return of more varied and abundant benthic faunas. At certain times and places, small but more architecturally intricate reefs re-emerge, built by new combinations of builders compared with pre-extinction times. These early reefs may be geographically limited and smaller than later Mesozoic counterparts, but they mark important steps toward re-establishing high-complexity, shallow marine ecosystems. Through this period, the geographic pattern of recovery is uneven. Some basins and regions function as early centers of diversification, where conditions allow relatively rapid increase in biodiversity and ecological complexity. Others lag behind either because they remain subject to harsh climates, persistent anoxia or frequent disturbance, or because geographic barriers limit immigration of new taxa. High-latitude sectors may follow different trajectories than low-latitude interiors, or Tethyan margins reflecting local histories of temperature, moisture, and sea level change. In many reconstructions, full restoration of global biodiversity to levels comparable with late Permian or earlier peaks requires tens of millions of years extending well into the later Triassic. But within the earliest part of this interval, the focus falls on the initial establishment of simplified but functioning ecosystems. These early recovery landscapes, both terrestrial and marine, are characterized by low to moderate diversity dominance of tolerant and opportunistic taxa, and strong coupling to ongoing physical and chemical stresses, yet they also contain the seeds of later expansions. Within their soils, sediments and biotic structures, the early stages of renewed ecological complexity unfold under the still distinctive climatic and geographic conditions imposed by a world that remains shaped by the presence of Pangea and its surrounding superocean. At the smallest scales, the record of the Pangean world and its harsh intervals is carried by grains, crystals, thin laminae, and microscopic fossils preserved in rocks that formed on land and in the sea. In marine sediments that span the late Permian into the early Triassic layers of mudstone and limestone often appear finely laminated with millimetre-scale alternations of lighter and darker material. Under magnification, these laminae can show little or no disruption by burrowing animals in intervals that correspond to low oxygen conditions, whereas older and younger layers may display mottled textures and disturbed fabrics where benthic organisms once mixed the upper sediment. The contrast between laminated and bioturbated layers at this fine scale marks changes in the presence and activity of seabed communities that do not always leave large body fossils. Within the same rocks, tiny crystals and mineral aggregates provide further clues. Frambodal pyrite, which forms as small raspberry-like clusters of iron. Sulfide crystals grows in environments where sulfate-reducing microbes operate under low oxygen or euxinic conditions. The size distribution and abundance of these framboids in particular layers indicate whether anoxic conditions were confined to the pore waters at the sediment surface or extended into the overlying water column. Layers with abundant, very small, uniformly sized framboids point to sustained water column anoxia, while larger and more variable grains suggest more limited or intermittent low oxygen conditions. These microscopic mineral features thus encode information about redox states in seas that bordered Pangea. Chemical signatures at the scale of individual carbonate grains and organic rich laminae also contribute to the reconstruction of environmental conditions. Ratios of stable isotopes of carbon within carbonate minerals and organic matter shift across the late Permian and early Triassic, and these shifts are recorded in the isotopic composition of tiny shells, cement phases, and macritic matrix. Thin section and microdrill sampling reveal that sharp negative excursions in carbon isotope ratios coincide with particular horizons that correspond to episodes of rapid carbon cycle disturbance, likely associated with large inputs of isotopically light carbon to the ocean atmosphere system. Oxygen isotope ratios in carbonates, while influenced by multiple factors, carry information about temperature and the composition of seawater, and patterns at high resolution across boundary intervals suggest changes in climate and hydrologic regimes. Sulfur isotopes measured in pyrite and sulfate minerals likewise record changes in the balance between microbial sulfate reduction, oxidation, and burial of sulfur species, reflecting shifts in oceanic redox and productivity. These isotopic variations are not visible to the naked eye, but they are locked within individual mineral grains and microscopic layers that formed in direct contact with seawater and pore water during the Pangean interval. In addition to minerals, microfossils form an important part of the fine-scale record. Conodont elements, which are tooth-like microfossils from extinct eel-like vertebrates, occur as tiny phosphatic pieces in many marine sediments of late Permian and Triassic age. Their presence-absence diversity and morphological changes across stratigraphic levels help define the timing of events and track biological responses. In some sections, conodont assemblages show abrupt reductions in diversity at levels that coincide with major geochemical changes, followed by recovery phases characterized by a simpler set of forms. Radiolarians, foraminifers, and other small planktonic organisms leave siliceous or calcareous tests that, when preserved, can be examined in thin sections or picked from residues. Changes in test morphology, wall structure, and species composition across boundary layers reflect shifts in surface water conditions, nutrient regimes, and ocean chemistry. In fine-grained sediments deposited in lakes and coastal basins, spores and pollen grains from terrestrial plants accumulate. Their outer walls resist decay and can be isolated and studied under the microscope. Changes in the relative abundance of particular spore and pollen types across stratigraphic intervals show how land plant communities respond to climate and environmental stress. Some horizons display high proportions of spores associated with opportunistic or disturbance-tolerant plants, while others contain more diverse pollen assemblages from complex forest communities. These microscopic plant remains, counted grain by grain, provide a detailed record of vegetation changes across the Pangean landscapes. Evidence for wildfire appears as charcoal particles and inertinous macerals embedded within sediments and coals. Under reflected light or scanning electron microscopy, these fragments reveal diagnostic features such as homogenized cell walls and glossy surfaces produced when plant material is heated in the presence of limited oxygen. Variations in the abundance and size of charcoal particles through stratigraphic sequences mark shifts in fire frequency and intensity. In some late Permian and early Triassic deposits, layers enriched in fine charcoal suggest episodes when fires became widespread across Pangean vegetation, contributing to soil loss and changes in atmospheric composition. On the land surface, paleosols preserve microscopic structures that speak to climate and hydrology. Thin sections of ancient soils show patterns of clay coatings, carbonate nodules, root traces, and pore networks. In arid and semi-arid paleosols formed in Pangean interiors, micromorphology commonly includes calcite or other evaporate accumulations around pores and along horizons, indicating repeated cycles of evaporation and limited leaching. Root channels may be sparse or shallow, and the distribution of clay and organic matter is patchy. In contrast, paleosols from more humid belts show better developed aggregates, thicker clay coatings, and abundant, deeper root traces indicating longer periods of plant occupation and more continuous moisture supply. Shifts from one type of soil microstructure to another within vertically stacked profiles indicate changes in climate vegetation and landscape stability through time. In volcanic sequences associated with large igneous provinces, the fine-scale record includes alteration textures and glassy ground mass mineral veins and vesicle fillings. Cooling fractures in basalt are infilled by secondary minerals such as zeolites and carbonates, whose compositions reflect the chemistry of circulating fluids during and after emplacement. Thin layers of volcanic ash or tuffs interbedded with marine or terrestrial sediments contain shards and crystals that can be dated using radiometric methods applied to individual zircon grains. These ages anchor the timing of environmental changes to numerical scales and show how quickly certain transitions occur relative to the rate of volcanic activity. Ash layers also supply nutrients and reactive surfaces to soils and seawater, and their mineralogy and grain size distributions help reconstruct eruption styles and dispersal patterns. Some of the most subtle yet informative features are preserved in the textures of carbonate rocks deposited on shelves and platforms. Growth bands in skeletal material cement fabrics in pores and micrite envelopes around grains are sensitive to the chemistry and temperature of the water in which they formed. Microborings made by tiny organisms now filled with cement trace out networks of tunnels that record the presence of bioeroding communities. In intervals where ocean chemistry and biology are strongly stressed, these intricate structures can change in density and distribution, reflecting alterations in community composition and carbonate saturation states. Laminated microbialites display millimeter-scale layering of different mineralogical or textural types, which formed as microbial mats responded to fluctuations in light sediment input and water chemistry. Variations in lamina thickness, composition, and organic content through microbialite buildups document changes in local environmental conditions on timescales of years to decades during and after the crisis interval. Together, these microscale traces knit the larger narrative of Pangea's most severe environmental stresses into the fabric of the rocks. Grain size patterns, mineral textures, isotope ratios, microfossil assemblages, charcoal fragments, and soil micromorphology. Each capture specific aspects of temperature, oxygen, availability, acidity, moisture balance, and biological activity, because they form directly from interactions between physical, chemical, and biological processes. At the time of deposition or alteration, they preserve information that is not always evident from large-scale structures alone. By aligning changes in these small-scale indicators through sections that cross the late Permian and early Triassic, and by comparing them across different basins and environments, it becomes possible to trace how the deadliest interval in Earth's known history unfolds in detail within the rock record of a world ruled by a single supercontinent and its surrounding superocean.